Okay, in this video we'll be going through the 2019 electricity exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you've completed the question or get stuck, unpause the video to see how I go about getting the answer. Mobile contactless payment systems are used in shops and restaurants throughout New Zealand. The mobile payment machine contains a battery that can be recharged by connecting an external 9-volt DC power supply. The terminal voltage of the external power supply drops to 8.6 volts DC when the circuit draws 0.333 amps of current. Show that the internal resistance of the external power supply is 1.2 ohms. Alright, so we know our terminal voltage is equal to our EMF minus our lost volts. Okay, and remember our lost volts is the voltage drop due to our internal resistance. Okay, and so we have a terminal voltage of 8.6, and that's equal to our 9 volts EMF minus our lost volts. Okay, which we can denote as IR. Okay, I little r. Remember, little r is the internal resistance value, and that is what we're trying to find. And obviously, I is the current throughout the circuit. Okay, and so therefore IR is equal to 9 minus 8.60, and so IR is equal to 0.4 volts. Okay, and we can see here that the current is 0.333 amps, and so R is equal to 0.4 divided by 0.333, and so our internal resistance is equal to 1.2 ohms. And as you can see, that is the value that we're trying to find. While it is recharging, the payment machine displays a charging symbol on the screen. The diagram shows a simplified model of the charging circuit at one moment in the recharging process. Using Kirchhoff's laws, determine the EMF of the rechargeable battery at this moment. Your solution should include an equation showing the relationship between I1, I2, and I3 at the junction A, and a calculation to show that I3 is equal to 0.2 amps. So, by Kirchhoff's current law, we know that all currents leaving a node is equal to 0. Okay, and so therefore, as we can see, we have one current entering the node, okay, and that's I1, and two currents leaving the node, which is I3 and I2, okay? And so therefore, I1 is equal to I2 plus I3. So the first loop for our voltage law, we can use this outer loop right here, okay? So as you can see, we have a 9-volt rise, all right? And then we have a voltage drop across this resistor, and that voltage drop is going to be equal to the current, which is I3, multiplied by the resistance, which is 18 ohms, okay? And once more, we have another voltage drop of this display, and that's minus I3 times the resistance, which is 25 ohms, okay? And we also have another voltage drop for the internal resistance, and so that is our current, which in this case, it's I1, so that's 0.333 multiplied by its resistance, which is 1.2. And also, as we just found in the previous question, this value right here is equal to 0.4, okay? So if we want, we can replace this value with 0.4, like so. And this all should equal 0. And so we get 9 minus 18 I3 minus 25 I3 minus 0.4 is equal to 0. And so 8.6 minus 43 I3 is equal to 0. 8.6 is equal to 43 I3. 8.6 all over 43 is equal to I3. And so therefore I3 is equal to 0.2 amps. And so we've shown that the current in I3 is 0.2 amps. All right, so we've ticked off both of these criteria. And so now that we know that I3 is 0.2 amps and we know that I1 is 0.333, we can now find the value of I2. Okay, and so 0.333 minus 0.2 is equal to I2. And so 0.133 is equal to I2. So now in order to determine the value of this EMF, we can use this loop right here. Okay, so once more, we have a 9-volt rise. Okay, so that's a 9-volt rise. And then we can minus this EMF because these are pointing in opposing directions. Okay, so we minus this EMF. We will have a voltage drop from this resistor right here, and that is equal to I2, which we just determined was 0.133, multiplied by the resistance of 9.8. So that's minus 0.133 multiplied by 9.8, okay? And then once more, we have a voltage drop of the internal resistance, which we already established was 0.4, and that's all equal to 0. And so as you can see, we have one unknown, so we can just rearrange, and we'll get the value of this EMF. So we get 9 minus EMF minus this value right here, which is equal to 1.3034 minus 0.4, and that's all equal to 0. And so therefore 7.3 minus our EMF is equal to 0, and so therefore 7.3 volts is equal to our EMF. And there we go. The circuit inside the contactless card does not have its own power source. It is powered by induction using a pair of coils, one in the contactless card and the other in the payment machine. A simplified model is shown in the diagram below. The payment machine's induction coil has an alternating current of frequency 13.6 times 10 to the 6 Hz. Using physics principles, explain how a voltage is induced in the coil of the contactless card when it is placed near the coil of the contactless payment machine. No calculations is required. So the alternating current in the payment machine will induce a changing magnetic field within the payment machine's coil. When the coils of the contactless card is close enough to the coils of the payment machine, the changing flux within the payment machine will result in a changing flux within the contactless card, thus inducing an EMF within the coils of the contactless card. And so you can write that in. At the frequency 13.6 times 10 to the 6 Hz, the contactless card's induction coil has a reactance of 427 ohms. The contactless card circuit contains a capacitor in series with a coil that causes the circuit to resonate only at this frequency. State the conditions under which resonance occurs and calculate the capacitance that is needed for resonance. Alright, so resonance occurs under the condition that the reactance of the inductor is equal to the reactance of the capacitor. Okay? And so in order to calculate the capacitance needed for this resonance to occur, we already have the reactance of the inductor, okay? And so therefore, the reactance of the capacitor must be equal to the reactance of the inductor, which is 427 ohms, okay? And we know that the reactance of the inductor is equal to 1 all over omega c, okay? Where our omega is equal to 2 pi f, and so therefore 427 is equal to 1 all over 2 pi f multiplied by our capacitance. We have a frequency of 13.6 times 10 to the 6, so 427 is equal to 1 all over 2 pi times 13.6 times 10 to the 6 multiplied by our capacitance. And so therefore, our capacitance is equal to 1 all over 427 multiplied by 2 pi times 13.6 times 10 to the 6, and that is all equal to 2.74 times 10 to the negative 11 farads. There we go. Inductive loops are also used to sense the presence of cars. Inductive loops are wire coils embedded into the surface of the road and are powered by an AC supply of known voltage and frequency. One particular inductive loop has 4 ohms of resistance and is powered by a 24 volt RMS voltage with a frequency of 1.2 times 10 to the 2 Hz. The loop is 1.6 meters by 0.6 meters in a rectangular shape with 3 coils of wire. Calculate the peak voltage of this power supply. Alright, so VRMS is equal to V peak all over root 2. If you don't know where this equation comes from and you're wondering, I have a video on it on my electricity playlist, so you can go check that out. But essentially, to calculate the peak voltage, we just need to rearrange. So we have V peak is equal to V RMS multiplied by square root 2. And so therefore we have a RMS voltage of 24 multiplied by root 2. And this gives a peak voltage of 33.94 volts. The strength of the magnetic field inside the loop is 0.0413 teslas. Calculate the maximum magnetic flux in each of the 3 coils of wire in the inductive loop. Alright, so we know our flux is equal to the magnetic field strength times our area. Okay, we have the dimensions of our rectangular shape, and so our dimensions are 1.6 meters times 0.6. Okay, and so this gives an area of 0.96 meters squared. Okay. Our magnetic field strength is given, and so we just simply have to plug in our numbers, like so, and this gives a value of 0.0396 Webers. When a car drives over the inductive loop, the steel in the car's body and engine interacts with the magnetic field of the inductive loop. The overall effect of this interaction is to reduce the inductance of the loop. Explain the effect decreased inductance would have on the current in the circuit. Alright, so if we reduce the inductance of the circuit, we know that the reactance of our inductor is equal to omega L, okay? Where obviously our L in this case is our inductance. And so if our inductance decreases, therefore the reactance in the circuit will decrease, okay? And so if our reactance decreases, therefore our total impedance will also decrease. And so therefore as V is equal to IZ, if our total impedance decreases and our voltage remains the same, therefore our current must increase. And so you can put that in words. Now, one thing to keep in note, what I just explained is pretty much essentially what the marking schedule wants. However, if you were to go onto the marking schedule for this paper, you will see in the merit column, it says something about linking magnetic flux with the induced voltage and induced current. And so that is the physics behind this concept right here. However, it does not ask that in the question. And also the model answer has nothing about that. It just has that on the merit column on what to tick. So what I'm saying is, The question didn't ask for it, and the model answer doesn't have anything about the magnetic flux and how that reduces inductance. However, it's one of the requirements in order to get merit for this question, and so to be honest, I have no idea whether or not you need that for the question or not. I'm going to hedge on the fact that because it didn't actually ask for that, you don't actually need it. But if you would like to know the reasoning behind this, this is very, very similar to how transformers work. Not exactly the same, it's not the exact concept, but the idea of inducing a voltage from an AC power supply onto another coil, that's pretty similar to what transformers do. And also, a question very similar to this has been brought up in another exam. I think it's, let me check. It is the 2015 exam, okay? And it is the very, very last question on that exam. And so if you want to know what is actually happening in this, I recommend attempting the 2015 exam. And also I have made a video on the 2015 exam if you want my explanation. The new inductance is 5 times 10 to the 3 henries. Determine the RMS current in the circuit. Alright, so the frequency is given all the way up here. Okay, so that's 120 hertz. Okay, so our frequency is equal to 120 hertz. Our new inductance is equal to 5 times 10 to the negative 3 henries. Okay, and so therefore we can find the reactance of our inductor as omega is equal to 2 pi f, okay? So therefore our reactance of our inductor is equal to omega L, and so that's equal to 2 pi f multiplied by L, and so that is equal to 2 pi times 120 multiplied by 5 times 10 to the negative 3. And so this gives a reactance of 3.77, or we could say that this is 6 pi all over 5, okay? So in the calculations, I'm going to use this value in order to keep whole numbers, okay? And if we go all the way up here, we can see that we have a resistance of 4 ohms, okay? And so our resistance value is 4 ohms. And so therefore our total impedance is equal to square root 6 pi all over 5 squared plus 4 squared. And so this gives a total impedance of 5.5 ohms. And so therefore V is equal to IZ. We have a VRMS current of 24 volts, okay? And so therefore I is equal to V all over Z, and that's equal to 24 all over 5.5, and that's equal to 4.37 amps. There we go. Capacitors built into rubber speed bumps can be used to sense the number of cars entering and leaving parking buildings. One particular speed bump capacitor consists of two 0.687 meter squared metal plates. When no car is present, the plates are separated by 0.0519 meters of air. Show that the capacitance of the capacitor is 1.17 times 10 to the negative 10 farads. Alright, so the equation for our capacitance is equal to the permittivity of free space times our dielectric constant times our area all over our distance. Our dielectric constant is given as 1 because we have our dielectric of air. The area is given, and obviously the permittivity of free space is given in your formula sheet, and we're also given the distance. And so we can simply plug in our numbers, 8.85 times 10 to the negative 12 multiplied by 1 multiplied by 0.687 all over 0.0519. And so this gives a capacitance of 1.17 times 10 to the negative 10 farads. The capacitor is connected to a sensing circuit as shown below. When the switch is closed, the current will begin to flow and charge the capacitor plates. Sketch a graph to show how the current changes from when the switch is closed to when the capacitor is fully charged. Calculated values for at least 2 data points should be included. Alright, so to find out our max current, okay, that is equal to the voltage divided by the resistance. The voltage in this case is 6 volts, and the resistance is 12 ohms. Okay, so that's 6 all over 12, which is equal to half, which is equal to 0.5 amps. And so therefore the max value on our graph is going to be equal to 0.5 amps. Okay, and so obviously this value right here is going to be 0, and this value right here is going to be 0.25 amps. Okay, now we can find our time constant of this circuit, as our time constant is equal to the resistance times the capacitance. We have, again, a resistance of 12 ohms times our capacitance of 1.17 times 10 to the negative 10, and that gives a time constant of 1.4 times 10 to the negative 9 seconds. And so we can separate the x-axis into 5 different quadrants like so, and so we get 1 time constant, 2 time constant, 3 time constant, 4 time constants, and then 5 time constants, okay? Where again, our time constant is obviously 1.4 times 10 to the negative 9 seconds, okay? And so now, to find our data points, we can take our max current and multiply it by 0.37 to find the current after one time constant, and that's equal to 0.185. And so that's going to be roughly over here, okay? And now after two time constants, the way we do that is we take our original max value and we multiply it by 0.37 squared, okay? And that's equal to 0.068 amps, okay? And so that is roughly right over here, okay? And we can do one more times 0.37, that's cubed, and that's equal to 0.025 amps. And that is roughly over here, okay? And obviously we're going to have this exponential decay like so. There we go. After the capacitor has been fully charged, a car passes over the speed bump. The weight of the car pushes the capacitor plates together, increasing the capacitance to 2.3 times 10 to the negative 2 farads. Assume the amount of charge on each of the plates at this moment is unchanged. Show that the voltage of the capacitor at this moment is 3.05 volts. Alright, so if the charge is unchanged, we know that Q is equal to CV, okay? And so that means the new capacitance multiplied by the new voltage must be equal to the charge, and this charge must still be equal to the old capacitance multiplied by the old voltage, okay? And so what we can essentially say is that the new capacitance multiplied by the new voltage is equal to the old capacitance multiplied by the old voltage, okay? And what we want to find is the new voltage, okay? So the new voltage is equal to the old capacitance times the old voltage all over the new capacitance. The old voltage, as we saw, was 6 volts, and the old capacitance was 1.17 times 10 to the negative 10, okay? So the old voltage was equal to 6 volts, and the old capacitance is equal to 1.17 times 10 to the negative 10 farads, okay? And we are given the new capacitance. And so therefore, we can just simply plug in our numbers, like so, and this gives a new voltage of 3.05 volts. And as you can see, that is the value that we're trying to find. Explain the effect the new capacitor voltage will have on the readings recorded by the ammeter and voltmeter 2 immediately after the capacitor plates are pushed together. Calculate the maximum current throughout the circuit. Alright, so I bored over the diagram. As we can see, this is the voltmeter 2, and this voltmeter is measuring the voltage across the resistor, okay? Alright, so when the plates are pushed together, due to this equation right here, okay, as our distance is now decreased, therefore our capacitance is going to increase, okay? And as our capacitance is equal to the charge all over the voltage, because our charge remains unchanged, if our capacitance increases, therefore our voltage across this capacitor V1 must decrease, okay? And so now, the voltage across the capacitor is no longer equal to the voltage of our power supply. And so that means charge will begin to flow onto the capacitor, and so now there is a current present in the circuit, okay? Remember before, when the capacitor is fully charged, there is no current flowing in the circuit because there are two equal opposing EMFs, and so no current will flow. However, now that the voltage across the capacitor has now decreased, it is no longer equal to the voltage of the power supply, and so now charge will begin to flow into the capacitor, and so there will be a current present. And so this means that the amp meter will detect a flow of current, okay? Also, because the voltage across our capacitor has now decreased, and we obviously know that this is a series circuit, and so therefore the voltage across components is shared. If there's a decrease in voltage across the capacitor, therefore momentarily there will be a voltage reading across V2. Remember, initially, when there is no current flowing, the voltage across the capacitor is equal to the voltage of our EMF, okay? And so therefore, there is no voltage across our V2, our resistor, okay? However, again, because this voltage decreases, and the voltage still needs to be shared across the components, therefore there'll be a reading across this amp meter, okay? However, that's only momentarily, because remember that capacitor is still beginning to charge because current is flowing, and so eventually the capacitor will become fully charged again and there will be no reading across this voltmeter, okay? And so we can calculate the maximum current throughout the circuit because we know that V is equal to IR, and so I is equal to V all over R. We know that the voltage across the capacitor at this moment is 3.05 volts, okay? And we know that the voltage across the EMF is 6 volts, and so therefore the voltage across V2 is equal to 6 minus 3.05, and that's equal to 2.95 volts, okay? And so therefore, 2.95 divided by our resistance of 12 ohms is equal to 0.246 amps. And with that, we're done.